Let's dive into Amazon's machine learning service next. Honestly, there are some more modern and better services in AWS for machine learning these days. This is one of the first ones, and it's somewhat limited. It can only do linear and logistic regression, and we'll talk about what that is shortly. For now, though, the exam does expect you to know what Amazon's ML service does, even if it's not the most popular choice these days. So let's dive into it. But whatever service you're using, it helps to know what machine learning is. So let's start off by talking about what machine learning is all about. Machine learning 101, if you will. So what is machine learning? Well, machine learning systems predict some unknown property of an item given its other properties, and this makes more sense in the context of some real examples. For example, you might want to know how much your house will sell for, most likely, and you could actually predict the sale price of your house given historical data of other houses that are similar to it, right? So if I have a database of historical house sales for a given zip code, maybe I can look for correlations between the number of bedrooms and the square footage and what amenities that house has, and compare that to the actual known sale price for that house. I can use a model built off of that data to predict the sale price of my house, given its attributes such as its square footage, number of bedrooms, zip code, and whatnot. Machine learning can also be used to do image classification. So I might be able to train a machine learning system using a bunch of images of things where I know what it is. And if I give it enough pictures of a house and enough pictures of a sign to learn from, maybe I could feed it this random new photo and it would say, hey, this photo contains a picture of a house and a picture of a sign. That's another example of machine learning. It also has applications in the medical field. So let's say I feed it a database of known biopsy results where I have a biopsy test done on someone and we're trying to figure out if that biopsy test is malignant or benign. If I have enough of a history of the properties of those biopsies and whether or not a real doctor determined they were malignant or benign, I could train a model to automatically predict whether it's malignant or benign based on new biopsy results that it's never seen before. And a very important application in the financial world is trying to flag financial transactions as fraudulent or not. So based on the attributes of a financial transaction, such as where the transaction took place, the amount of the transaction, and who did it, I might be able to automatically flag a credit card transaction as potentially being a fraudulent transaction and sparing both the bank and the customer a lot of hassle by catching that early on. These are all real-world examples of machine learning and how it's being used today. There's a lot of different ways to do it, and we're just going to talk about one for now. The intersection with big data, though, is pretty obvious, though. So these algorithms themselves can be fairly complex, and they get even more complex when you're throwing massive amounts of data at it. So imagine, Bank of America. They have massive amounts of data on credit card transactions, right? So this is both a machine learning problem and a big data problem when they're trying to find fraudulent transactions. Typically, we talk about supervised learning in these sorts of systems, and supervised machine learning systems are systems that are trained using historical data like we talked about. So let's get some nomenclature out of the way here first, all right? So the property you're trying to predict, such as what object is in this picture or what is the sale price of this house, that's called the label of the data. So the label is the thing you're trying to predict. Now you're going to feed your supervised machine learning system a training data set. And this is a data set of historical information that contains labels that are known to be correct together with the other known attributes of that data. So going back to the predicting a house price example, we might have a training data set of historical house prices that have known numbers of location, number of bedrooms, square footage, and whatnot. So our training data set knows all the attributes of every house, and it also knows the answer. It knows the label of each one of those houses, which is the sale price that we ultimately want to be able to predict. So we take all that training data and we use it to build a model that tries to find these relationships between the attributes and the labels. And we can then use that model to make predictions of unknown labels on new data. So we can take a model that was trained using the known sale price of past houses and use that model to predict the sale prices, which we don't know yet, of houses that are just going onto the market for the first time. That's how supervised learning works. It's basically training a model based on historical information and using that model to make predictions about new data where we don't know the answer. So how do we evaluate how good a supervised learning model is? Well, one way is by using something called train test. And the idea here is that you take your training set, your historical data, and you split it into two sets randomly. One you're going to call the training set, and this is usually the bulk of your data, and the other will be your test set. The idea is to set your test set aside so that when you're training your model, it doesn't know about that information at all. And then later, after you've built your model, you can evaluate how well your model is able to predict the known labels in that test set that you set aside. So basically, you're training your model on a set of data and then testing it on data that it's never seen before, that it doesn't know the answers to already, that it has no foreknowledge of. And if your model is able to accurately predict the labels in that test set that you set aside, you can measure how good your model is at predicting unknown data. Now, you can measure that by any number of accuracy metrics. A popular one, for example, is RMSE, or root mean squared error. So let's talk about the house price example again, for example. Let's imagine that we have our historical data of sale prices of houses in the past, and we know all of their number of bedrooms, the year the house was built, the location, and all that stuff, and we know the prices that each house sold for. We would take that entire data set, say we have 1,000 historical sale data points there to work with. Maybe we take 800 of those and use those for training our machine learning model. We would reserve the other 200 as a test set. So we take those 800 points from our training set, build a model to build up that relationship between the attributes and the sale prices, which is our label. And then once we have that model, we'll take our remaining 200 data points in the test set. We will not tell our model what the answer is, what the labels are in that known test set. So we'll say, okay, model, here's 200 more houses, and here's the number of bedrooms, the zip code, the square footage of all these houses. Tell me what you think the sale price would be. And it will come back with a number, and we can compare that to the known actual sale price for each one of those and measure how accurate our model really is.